Hello friends, welcome to a new video of I Square. In the previous class, we have discussed exercise 1.1 of your chapter 1 sets. And in today's class, we are moving with the chapter and we are going to learn some types of sets. And the first type of set is empty set. From the word itself, we can assume that what will be the definition of an empty set. The word empty means there is nothing, and an empty set means a set which contains no elements. For example, consider the set of prime numbers between 14 and 16. Consider the set of prime numbers between 14 and 16. We know that there is only one number between 14 and 16, and that is 15. And now we have to check whether 15 is a prime number or not. We know that the factors of 15 are 3, 5, 1, 15. These are the factors. And if 15 is prime, there exists only only two factors, that is 1 and 15. Here, but there are two more factors, 3 and 5. So it is clear that 15 is not a prime number, and therefore there is no number which satisfies this condition, that is set of prime numbers between 14 and 16. Therefore, we will denote that particular set. Let's call this set as A, and now we can, this is the set builder form of the set, and in roster form when we write that set, there will not be any element in that set. Therefore, we will call that an empty set, and it can be denoted like this. Or it can be also denoted as using this symbol, that is phi. So an empty set is something or a set which does not contain any element, and it can be denoted using the empty braces or this notation which is read as phi. So that is the definition of an empty set. Now let's check whether these sets are empty sets or not. Now check whether the set A is an empty set or not. Set A is set of all x such that 1 less than x less than 2, where x is a natural number. That is, the set of all natural numbers between 1 and 2 is our set A. Now, it is clear that there is no natural number between 1 and 2. Our first natural number is 1 and the second natural number is 2. So, there is no natural number between 1 and 2. So, there is no natural number satisfying this particular condition. So, our set A is an empty set, and we denote it using the symbol phi or the empty set braces. Now, moving on to the second example. Set B. B is the set of all x such that x square minus 2 equals to 0. All the x's should satisfy the condition x square minus 2 is equal to 0. Now, the x satisfying that condition is x square minus 2 equals to 0 implies x square is equal to 2, and which implies x is equal to plus or minus root 2. So, these plus root 2 and minus root 2 is the set of all x satisfying this condition x square minus 2 equals to 0. But we have one more condition, that x is a rational number. It is clear that both plus root 2 and minus root 2 are irrational numbers. Therefore, there is no number satisfying this condition, which means set B is also an empty set, and we denote it using our symbol phi. Now moving on to the third question. C is equal to set of all x such that x square is equal to 4 and x is odd. Now we know that the set of numbers, that is the set of x satisfying x square is equal to 4 is x square is equal to 4 implies x is equal to square root of 4, and it is plus or minus 2. Now, it is given one more condition, that x should be odd, but we know that plus or minus 2 is even. Therefore, there is no odd number satisfying this particular condition, x square is equal to 4. So, in this case also, our set is an empty set, and we can denote it also like the empty braces. Now, that's it. Now, let's discuss what is a finite set. Before defining what is a finite set, it is necessary to understand what is the cardinality of a set. Now, defining the cardinality of a set, let's consider the first example given here. Set of days in a week. The set W is the set of days in a week. We know that in a week there are 7 days, and they are Sunday, Monday, Tuesday, Wednesday, Thursday and Saturday. These are the weekdays or the days in a week. So, this is the required set. And in this set, the cardinality can be defined as the number of elements in the set. And in this set, the number of elements is 1, 2, 3, 4, 5, 6. So, the cardinality of set W or the number of elements in set W is 7. So, the cardinality of a set is nothing but the number of elements in the set. Always remember one more thing, that we always count the number of distinct elements in the set. That is, if a number or an object or an element in a set is repeated again and again, we always never count the repetition count. We only count the number once. So, in this set, no elements are repeated, all the elements are distinct. Therefore, the number of elements is 7. So, the cardinality of set W is 7. Now, in this example, set of solutions of x square minus 16 equals to 0. And we know that the solution of x square minus 16 is found like this. X square is equal to 16, which implies x is equal to plus or minus 4. So, in this set, we have only 2 elements, that is plus 4 and minus 4. And both plus 4 and minus 4 are distinct elements. So, cardinality of this set S or the number of elements of this set S is 2. Now, in both of these examples, let's check what is the cardinality. Here it is 7 and here it is 2. And in both examples, the cardinality or the number of elements is a definite number. In this case or in this position, we can define what is a finite set. A finite set is a set whose number of elements or the cardinality is a definite number. Here it is a definite number, that is 7, and here it is a definite number, that is 2. So, a finite set can be defined like this. A set is said to be finite if it has if the number of elements in the set is a definite number, or there is one more condition, or the set is empty. So, in total, a set is called a finite set if it has a definite number of elements or it is an empty set. Moving on to the third example, set of points in a line. We know that this is a line and we cannot count the number of elements or the number of points in a line. We cannot denote a definite number to tell the number of points in a line. So, the cardinality of this set, that is the set of points in a line, is not a definite number. So, it is not a finite set. A set which is not finite is called by a name, that is infinite set. So, what is an infinite set? A set which is not finite is called an infinite set. So, this particular set is an example for an infinite set. Both of these sets are finite sets because the cardinality or the number of elements is finite or it is a definite number. Now, moving on to the fourth example, set of natural numbers. We know that the natural numbers are 1, 2, 3, 4 and it goes like it. We cannot count what is the we cannot count the number of elements of the set of natural numbers. It goes like that. So, the cardinality of this particular set or the number of elements of this particular set is not a definite number, which means that it is not a finite set. If a set is not finite, it is called an infinite set. So this is also an example of an infinite set. So these two sets are infinite sets and these two sets are finite set. A finite set is a set which contains a definite number of elements, or it is an empty set, which means all the empty sets are finite sets. Now, what is an infinite set? A set which is not finite is called an infinite set. Now, let's check whether these sets are finite or not. Considering the first question, set of all x such that x belongs to n. This bold n is always used to represent the set of natural numbers. Please remember this notation. This is very important. It is always used in your textbooks. Bold n is always used to represent the set of natural numbers. So here, set of all x such that x belongs to n, that is x is the set of natural numbers. X is a natural number and x minus 1 into x minus 2 equals to 0. We know that the natural numbers are 1, 2, 3, 4, etc. And it also should satisfy one more condition, that is x minus 1 into x minus 2 equals to 0. We know that the solution of this particular equation is x is equal to 1 or x is equal to 2. Sorry, x is equal to 1 and x is equal to 2. So, the set with the natural numbers and satisfying these condition is only 1 and 2. So, this is the roster form of the set, that is set 1, 2. Now, what about the cardinality or the number of elements of the set? We can count it easily, 1, 2. So, there are 2 elements in the set. So, 2 is a definite number and we can therefore say that this set is a finite set. Now, in the next example, we have set of all x such that x is a natural number and 2x minus 1 equals to 0. Natural numbers are these numbers and it should also satisfy one more condition, that is 2x minus 1 equals to 0. We can solve that equation, that is 2x is equal to plus 1 and x is equal to 1 by 2. Here we got x is equal to 1 by 2. So 1 by 2 is the only solution of this particular equation. But we know that 1 by 2 does not belong to the set of natural numbers because natural numbers are 1, 2, 3, 4, 5, 6, etc. And 1 by 2 is not a natural number. So we cannot find any element satisfying both of these conditions, which means this set contains no elements, which means this set is an empty set. What about an empty set? Is an empty set a finite set? Yes, of course, an empty set is always a finite set. So this is also a finite set. Now, moving on to the third question, set of all x such that x belongs to n, that is x is a natural number and x is prime. X is a natural number, we know that these are the natural numbers. And what are the prime numbers? Prime numbers are also going infinitely, that is 2, 3, 5, 7 and it goes like this. We cannot assure that what is the last prime number or what is the last natural number. So this is also an infinite collection. So or we can say that we cannot count what is the total number of prime numbers existing. So this is also, so the cardinality of this particular set is not a definite number. So this is an infinite set. Now, what about the fourth question? Set of all x such that x belongs to n, that is x is a natural number and x is odd. So we know the odd numbers are 1, 3, 5, 7, 9, etc. and it goes like it. Now, we cannot find the total number of elements here also. It cannot be a definite number. So, it is not finite, which means the set is infinite. So, that's all about finite and infinite set. Now, we are going to discuss what are equal sets. So what are equal sets? Let's consider this example. What is the set A here? It contains the elements 1, 2, 3 and 4. What about the set B? Here it contains the elements 3, 1, 4 and 2. Two sets A and B are said to be equal if every element of A is in B and if every element of B is in A. Let's discuss it more. If 1 is in A, that is if 1 belongs to A, then 1 should belongs to B also. Here 1 is in A. Now let's check whether 1 is in B. Yes, 1 is in B also. Now what about 2 here? 2 belongs to A. Now we want to check whether 2 belongs to B. Yes, 2 also belongs to B. So 2 belongs to B. Now 3 belongs to A. We know that 3 belongs to A. And here also there is 3. That is 3 belongs to B also. Now here there is 4. We know that 4 belongs to A. And here we have 4 here. No. Now that is 4 belongs to B also. Which means that every element of A is there in B. Now checking the converse part, every element of B should be there in A. Here 3 belongs to B and 3 is also here. 3 is also here. Now 1 belongs to B, 1 is also here. 4 belongs to B, 4 is also here. 2 belongs to B and 2 is also here. So in this example, every element of A is in B and every element of B is in A. In such a case, these two sets A and B are said to be equal sets and we denote them by A equal to B. An equal set is a set or two sets are said to be equal if every element of A is in B and every element of B is in A. Also there is one more condition that the cardinality or the number of elements of both the sets will be always equal. So two sets A and B are said to be equal if the cardinality of both the sets are equal and every element of A should be in B and every element of B should be in A. Now let's check whether X and Y, the sets given here X and Y are equal or not. X is the set of prime numbers less than 6. What are the prime numbers less than 6? They are 2, 3 and 5. So this is the set X we have. Now what about the set Y? Set of prime factors of 30. We know that the factors of 30 are 1, yes, 3, 2, 5, 6, 15 and 30. So these are the factors of 30. Now which are the prime factors here? 3 is prime, 2 is prime and 5 is prime. No other factors are prime. So the required set is 3, 2 and 5. Here what is the cardinality of this set? The cardinality is 3. Here what is the cardinality? The cardinality is 3. So now the first condition is okay. Both the sets have same number of in both the sets the number of elements is same. Now let's check whether every element of X is in Y or not. Here there is 2, here there is 2, here there is 3, here there is 3 and here there is 5, here also there is 5. So every element of X is there in Y. Now let's check whether every element of Y is there in X. Here we have 3, here also we have 3, here we have 2, here also we have 2, here we have 5 and here also we have 5. So every element of Y is there in X. So we can clearly say that X equal to Y or X and Y are equal sets. So when are two sets called equal sets? Two sets are said to be equal if every element of the first set is in the second set, and every element of second set is in the first set, and also the cardinality or the number of elements of both the sets are equal. In this question, we are going to check which of the following pairs are equal, and the first set is set A and it contains only one element, that is 0, and second set is set B. It is the set of all x such that x greater than 15 and x less than 5. That means x should be a number which is greater than 15 and less than 5, and we know that there is no number like that which is both greater than 15 and less than 5. So we can conclude that this set contains no element, that is, this is an empty set. It can be denoted using this empty brackets or the letter 5. Now, C is the set of all x such that x minus 5 equals to 0. It is clear that x minus root of this particular equation is x minus 5 equals to 0 is x is equal to 5. So, it is our set 5 which contains only one element, that is 5. And here also set of all x such that x square is equal to 25. It contains the roots of x square is equal to 25, that is plus 5 and minus 5, because plus 5 square is 25 and minus 5 square is also 25. So it contains two elements, that is plus 5 and minus 5. Moving on, the set E is the set of all x such that x is an integral positive root of x square minus 2x minus 15. So we have to find the root of this particular quadratic equation, x square minus 2x minus 15 equals to 0. We can solve this using splitting the middle term, and the middle term is minus 2x, and it can be splitted like this: minus 5x plus 3x minus 15 equals to 0. Now we can take x common from here, that which become x into x minus 5 plus, here we can take 3 as common, so we will get 3 into x minus 5 equals to 0. So it will become like this: x plus 3 into x minus 5 equals to 0. So the roots of this particular equation are x is equal to minus 3 and x is equal to 5. Now x is an integral positive root of x square minus 2x minus 15. So we cannot consider this particular negative root, that is x is equal to minus 3. So the only possible root which satisfies the condition given by the set is x is equal to 5. So our set E is nothing but the set 5. Now we can check which of the following sets are, pairs of sets are equal. Now set A contains 0 only, and we can see that no other set B, C, D and E contains the element 0. So we can clearly say that A not equal to B, A not equal to C, A not equal to D and A not equal to E. Now our second set B is an empty set and no other set is an empty set. So we can say that B not equal to A, it's clear, B not equal to C, B not equal to D and B not equal to E. Now we will consider our second set, that is set C, and it contains only one element, that is 5. So a set which is equal to set C is the another set which contains only one element, that is 5, and we know that set E is that particular set which contains only one element. Look, for E and for C and E, here we have 5, here also we have 5, here we have 5 and here also we have 5. So every element in set C is in E and every element in set E is in C. So we can say that set C equals to E. Now we have to check set C equal to D. No, because 5 is in C and 5 is in D, but minus 5 is in D but minus 5 is not in C. So we can say that C not equal to D. Now consider D. D is not equal to E because here we have plus 5, here also we have plus 5, but here we have minus 5, but here we do not have minus 5. So we can clearly say that D not equal to E also. So the only equal sets are C and E, and they are equal, C equal to E, and it contains only one element, that is 5. Now let's check some more examples to check whether they are equal sets or not. Now in this question we have to check which of the following pairs are equal, and we have to give the justification for our answers. And in the previous questions, all the previous questions we have discussed in today's class, we are given with the justifications, and always be careful while doing the justifications and writing the justifications. Now here the first pair is set X and set B. What is the set X? X is the set of letters in the word alloy. Which are the letters in the word alloy? It contains A. Yes, it contains 2 times L, but in set we have to write it only once. So L. Now we have O and Y. These are the letters in the word alloy. Now B is the set of all letters in the word loyal. Now in loyal we have L, again O, Y, A and L twice, so we don't have to write it again because we have already written L here. Now are these sets equal? We have to check the set X equal to B or not. How will we check two sets are equal? If every element of X is in B and if every element of B is in X, we will say that X is equal to B. Now here we have A, here we have A, here we have L, here we have L, here we have O, here we have O, here we have Y, and here also we have Y. So every element of X is in B. Conversely also, if we look like that, L is in here, O is it in here, Y it is here, A it is here. So every element of X is in B and every element of B is in X. So you can write that explanation. Every element of X is in B and every element of B is in X. Also you have to specify the sets X and B in roster form. Then you have to write every element of X is in B and every element of B is in X, and that is the justification for this particular question. Moving on to the second pair, we have A is equal to set of all n such that n belongs to Z and n square less than or equal to 4. What is Z? Z denotes the set of integers. Always remember, this is the letter we use to denote the set of integers. N belongs to Z means n is an integer. Now n set of all n such that n belongs to Z, that is n belongs to integer set, and we know what all are integers. Now n square should be less than or equal to 4. Also, as one more condition is given, the square of the integer should be less than or equal to 4 also. We know that integers are 0, 1, 2, 3 and go like that, minus 1, minus 2, minus 3 and go like this. Now we have to select some integers from this list which satisfies this particular condition that the square of the integer should be less than or equal to 4. We can take squares. Square of 0 is 0, square of 1 is 1, square of minus 1 is 1, square of 2 is 4, square of minus 2 is also 4. Now what is these all numbers satisfies the condition that n square less than or equal to 4. Now what is the square of 3? It is 9. What is the square of minus 3? It is again 9. So from 3 onwards to the positive infinity and minus 3 onwards to negative infinity, the square is greater than 4, and we can say that the numbers which satisfy our condition n square less than or equal to 4 are minus 2, minus 1, 0, 1 and 2. We are asked to write the integers whose squares are less than or equal to 4. In this line we wrote the squares and we are asked to find the integers whose squares are less than or equal to 4. So in our set the elements will be -2, -1, 0, 1 and 2, and we can easily say that the squares of these integers are less than or equal to 4. Now moving on to set B. Set B is the set of all x such that x belongs to R. Now what is R? R is the set of real numbers. R is the set of real numbers. We know what are real numbers. Real numbers are the collection of both rational numbers and irrational numbers. Now one more condition is given, x square minus 3x plus 2 equals to 0. So we have to solve that particular quadratic equation by splitting the middle term, and middle term is minus 3x. We can split minus 3x like this, x square minus 2x minus x plus 2 equals to 0. Now we can take x common from these two terms and remaining terms are x minus 2. Again we can take minus from these two terms, that is minus 1 into x minus 2 equals to 0. Now we can take x minus 2 common, then it will become like this, x minus 2 into x minus 1 equals to 0. That is product of two numbers are 0, which means either x minus 2 equals to 0 or x minus 1 equals to 0. So we have x is equal to 2 and x is equal to 1. So both of them are real numbers and also both of them are roots of this particular equation. So our set B is set element, and the elements of the set B are 1 and 2. So we got B and A, and here we have minus 2, minus 1, 0, 1 and 2. Here we have only 1 and 2. So here we have 0 belongs to A, but 0 does not belongs to B, which means every element of A is not in B. Therefore we can say that these two sets are not equal. So to say that these two sets are not equal, first of all we have to write the both sets in roster form, that is this form and this form, and then we have to say that 0 is in here but 0 does not belongs to B. Also minus 1 is here but minus 1 does not belongs to B. Minus 2 belongs to A but minus 2 does not belongs to B. This is the justification for these two sets are not equal. Now that's it. We have discussed what are equal sets in today's class, and we have solved many problems related to that. Now in the next class we will solve the exercise related to equal sets. Until then, wait for the next video. Thank you for watching. Bye bye.